Welcome to what would have been lecture 21 on April 8, 2020. Here is what would have been playing. And that is Phases and Stages from Willie Nelson back from 1974. And I picked this one because, well, we're talking about phases, or phase changes a lot in today's work. So let's get going. So this time between the 2 or 3 lectures, however they split up, we're going to be talking about phase transitions and their energetics and phase diagrams. This is in sections 10.3 and 10.4 in the text. By the time we're done today, you should be able to identify the main features of a phase diagram. You should be able to relate vapor pressure to the relative strengths of intermolecular forces. Using a phase diagram, you should be able to identify phase changes based on temperature, pressure changes, and also to calculate the energy involved in these, given heat capacities, phase changes, and a couple of other pieces of information. All right, so let's talk about a particular phase change, vaporization, boiling. So, and this is kind of what's going on in a molecular level. So let's say that you had a completely empty container, stylized right here, and you magically, with, I don't know, Star Trek transporter technology, beamed in a bit of liquid water, shown here. So what would happen is, at some point, some of these, there is an average energy for these guys. Some have more than the average, some have less. And it's quite possible that some that have more than the average energy, and that is near the surface, might actually have enough energy to break away from the hydrogen bonds that it has with its neighbors and release into the gas phase. And once that happens, it would do what gas phase molecules do. It would just kind of randomly move around until it either hits, until it hit another molecule or, the container. And maybe sometime later, another one undergoes this. And maybe 3. And maybe 4. Now, what would happen at that point is, while these things are randomly moving around, some of them might actually start to hit the surface of the liquid again, and they may or may not stay in the liquid. And at some point, the rate of escapes of water molecules from the liquid would equal the rate of recaptures from the gas into the liquid. And once that point is achieved, we say that these two phases are in equilibrium, that the relative amounts of both of them are the same. So, in these last two frames right here, there are 4 water molecules in the gas phase and umpteen of them in the liquid phase. Now, what you also need to understand is that any one water molecule is going to be going back and forth in between the liquid and gas phase, quite possibly a few billion times a second. But once equilibrium is reached, there's always going to be 4 of them in the gas phase and however many of them you've got in the liquid phase. And that ratio would not change until something else did, notably if you change the temperature. If you were to increase the temperature, you would get more of them in the gas phase because you have a higher average energy. And if you decrease the temperature for opposite reasons, you would get fewer of them in there. So this represents 2 phases being in equilibrium, in this case liquid and gas. The transition from one to the other, from the liquid to the gas, is called vaporization, or in colloquial English you call it boiling. And the opposite, going from the gas back into the liquid, is called condensation. So let's do this in math here. So equilibrium, we're going to talk a bit more about this in another chapter. This is a state where 2 different processes that essentially cancel each other out happen to occur at exactly equal rates. And usually talk about a process like this with some sort of double arrow like this. So I could express the equilibrium between liquid and gas with this double arrow saying that, well, liquid's going to gas, but at the same time, gas is going to liquid. But this actually is not quite right either. Usually chemists like equilibrium arrows to look like that. And so in one direction, the process is vaporization. In the other direction, we've got the condensation process going. What else do you need to know? So in any equilibrium, the reason why the relative amounts of the reactants and the products don't change is that both rates, forward and backwards, are exactly equal. And the other thing to know is that the gas produced by the evaporation, like all gases, well, they exert a pressure on the container walls and also on the liquid below it. Now, this pressure, or more specifically its magnitude, can actually tell us a bit about relative strengths of the intermolecular forces, just like we used the boiling point to a couple lessons ago. So here's an example. So what I've got here in this graphic is this is showing you the vapor pressure exerted by three compounds, methane, CH4, methanol, CH3OH, and water, at a variety of different temperatures. This is in degrees Celsius. And for clarification, 1 atmosphere of pressure is sort of noted right here. So I want you to look at this graph, and you can look at it in a couple of ways. One of them is, what the temperature at which the vapor pressure of these various compounds will be at 1 atmosphere. How much energy does it take to get 1 atmosphere's worth of molecules into the gas phase? So think about that and then tell me which one of these you think has the weakest intermolecular forces and which has the strongest intermolecular forces. All right, so the way that you want to think about this is the thermal energy needed to get 1 atmosphere's worth of methane molecules is a paltry, let's see, 120, 140, 160, about 165 degrees below 0 Celsius. So you do not need a whole lot of thermal energy to get 1 atmosphere's worth of methane molecules into the gas phase. Methanol, on the other hand, requires a temperature of, so this would be 40, 60, 80, let's call it 82 degrees Celsius. And water requires, doesn't get that pressure until 100 degrees Celsius. So the methane required by far the least temperature, the least amount of thermal energy to get that much, that many molecules in the gas phase. Water took the highest, and methanol is in the middle and much closer to water than it is to methane. So this is an experimental statement that that the intermolecular forces here are stronger because you need a lot more energy to break them. Now, could we predicted this? Is this kind of what we expected based on what we know about intermolecular forces? Well, let's look at the Lewis diagram for these guys. So this is the Lewis diagram for methanol. I'm sorry, that's methanol. The other one was methane, and here is water. So this is, and now let's think about the intermolecular forces that are available to each. This is all CH bonds. They are not polar, so there is no way that molecule is polar, which tells us that that has only London dispersion forces available to it. Methanol, on the other hand, is a polar molecule because of this carbon-oxygen bond and this oxygen-hydrogen bond. And here I've actually drawn lone pairs on the oxygen. So like any molecule, this has London dispersion forces available to it. It's polar, so it also has dipole-dipole interactions, but more importantly, you have a hydrogen bonded to an oxygen. So this hydrogen bonds, and that is going to be the dominant intermolecular force for this molecule. Now, what about water here? It's actually the same situation. there are London dispersion forces. It's polar molecule because of the oxygen-hydrogen bond, so there are dipole-dipole interactions at work here. But it also hydrogen bonds. And when you've got hydrogen bonding, that's usually by far the most significant intermolecular force. And you can also imply that the hydrogen bonding is actually a little bit stronger in water because of the difference in the temperatures at which you get the 1 atmosphere. So it looks like of the 3, water has the strongest intermolecular forces. So that's one way you can look at it. You can look at the temperature at which a particular pressure is achieved. Now you could have done half an atmosphere. You could have done 3 atmospheres and gotten the same ranking. Another way you can do this is by seeing what the vapor pressure of these molecules are at one particular temperature. So what you want to do in that case is look at a particular temperature, it doesn't really matter which one, where you've got data for both compounds here. Now, in this case, at, I don't know, 85 degrees Celsius, the vapor pressure of water is about, let's say, 0.65 atmospheres. And the vapor pressure of the methanol at that point is going to be about 2.4 atmospheres. So at a particular temperature, you've got a lot more of the methane molecules in the gas phase than you do in the water. And again, you can use that to imply that the intermolecular forces in methanol are weaker because than they are in water, because at a particular temperature there's way more of these guys in the gas phase than there are of this one. And since the vapor pressure of methane would be way off the scale in this case, you can infer there that those intermolecular forces are much weaker than what you've got in either one of these two. So you've got 2 ways you can look at it. The vapor pressure at the same temperature, in which case higher pressure, weaker intermolecular forces. Or you can look at the temperature at which a particular pressure is achieved. The higher the temperature to get to that pressure, the stronger those intermolecular forces are. So let me ask you a question. Would you expect water to boil at a higher or lower temperature if the altitude was higher? And for this, remember that boiling is merely defined as at the point at which the vapor pressure of whatever you're talking about is equal to the ambient pressure. And if you're boiling something like in an open pot, that is the atmospheric pressure. And now what you need to know here is that as altitude, and I'm sure you know this, as you go up in altitude, the vapor pressure or the atmospheric pressure actually drops. So the well-known boiling point of water being 100 degrees Celsius, typically this is called the normal boiling point of water. And that is defined as the temperature at which the vapor pressure of the thing is exactly 1 atmosphere, or 760 torr, depending on what units you like. And at sea level, that happens at 100 degrees Celsius. Now, what if you are boiling something at the 10-3 restaurant, for example, back when we could do that, which happens to be at the top of Sandia Crest? The vapor pressure there is roughly 70% of what it is at sea level. So that's about, in these units, it's about 532 torr. So this is the pressure, and then we want to look down to see what temperature the water is going to have that vapor pressure, and that is only 90 degrees C. So atmospheric pressure is about 0.7 atmospheres, about 530 torr, so that is incorrect. At 31 70 meters, which is about 10,300 feet, which is the altitude at the top of the Sandia crest. So the coffee at that restaurant might not be that good, because at that time that's the highest temperature you could get liquid water, and at that point it might not necessarily start to extract all the good tasting oils. I didn't get a chance to go there, so I cannot report for sure.